You just won the Super Bowl. What are you doing next?
I'm going to go to Disney World.
Washington Redskins just won the Super Bowl. What are you going to do next?
I'm going to Disney World!
And greetings. Welcome to the Evidence and Reasons for the Christian Faith video channel. I'm Salvador Cordova. It says in the Bible that the kingdom of heaven is like a hidden treasure, and sometimes finding God, evidence of God, is like finding a hidden treasure. It is by God's design that He's not totally apparent to our senses as the air we breathe. I believe that's partly so that we could show God who really wants to seek after Him. There are many things that people seek after, especially atheists, that they can't prove that it's the right thing to do, and they don't have any evidence. And yet, there is evidence for the Christian faith that Jesus Christ rose from the dead, and sometimes you have to go look for it. Now, people say, well, it'd be better if Jesus just appeared, and I'll say, well, it might be easier to believe, that is for sure, but compare how especially atheists who believe in naturalistic abiogenesis, and they have no proof that this can happen, and if there's no God, they have no way of proving what is right and wrong. They just follow whatever they want. So with that, we're going to cover some of the things. This is a little bit older article on the Big Bang. It's written by Michael Disney, hence I use the name Disney, the wonderful world of Disney. In the United States, there is Disney World, and it's an amusement park. It's probably the biggest in the world, the biggest in the universe, and it's just a place to go and just imagine and just participate and make believe and kind of escape the troubles of the real world for a little bit. So let me see here. Yes, I'm gonna share a Bible verse. Here in the United States, if you'll indulge me, here in the United States, it's the day to pay taxes. It's the deadline. So the Bible verse of the day, Romans chapter 13, 6 through 7. This is also why you pay taxes, for the authorities are God's servants, who give their full time to governing. Give to everyone what you owe them. If you owe taxes, pay taxes. If revenue, then revenue. If respect, then respect. If honor, then honor. And I don't mean to disrespect the scriptures, but today, April 18, 2022, is tax day, and it almost seems sarcastic to be quoting that Bible verse. So I don't know what to do about that. I don't mean to disrespect God's word, but I think a lot of us will laugh when we see that. It's like, okay, that's the Bible verse of the day. So with that, let me now go to just a reading of this, reading and commentary. I'll try to I'll try to minimize the commentary and just read through it, but sometimes I may have to pause just so I can process it or explain it. Sometimes explaining it even to myself is helpful. So let me just try to get this a little larger. There is a Wikipedia entry for Michael Disney. He's clearly a very respected astronomer. Oh boy, okay. I'm just trying to get all my buttons lined up here. Streamlabs is challenging to use. So let me try to get all this lined up. Modern cosmology. Science or folktale? Physics and Astronomy, Cardiff University, United Kingdom. And this is published, I believe, in something like one of the popular science articles too. So I'm just going to go through this and read. In a survey for non-astrophysicists, we compare the number of independent measurements which support Big Bang cosmology with a number of auxiliary hypotheses such as dark matter, dark energy, and inflation, and their associated free parameters needed to shore it up. We find such parameters still outnumber the relevant observations, with no real sign of an improving trend over time. Precision, which is improving, doesn't necessarily guarantee the soundness of the interpretation. Non-cosmologists are entitled to be skeptical of such a weakly supported superstructure, which is currently composed of 5 separate theories piled on top of one another. By the way, as I've mentioned in other talks, 3.5 scientists at my undergrad alma mater echoed these same concerns, especially about dark matter, dark energy, and inflation. At my graduate alma mater, there was Adam Rees at Johns Hopkins, who won the Nobel Prize for dark energy. So this is kind of a very strange situation for me as a physics student, where some of my professors are saying, no, that's bad stuff. And then another professor wins the Nobel Prize and says that's good stuff. And yet, at the same time, at that very same school, some of his colleagues quietly express reservations. And I'll just leave it at that, and no names will be mentioned. How could we find an answer? It appears everybody is interested in cosmology. For one of the more than 60 separate cultures studied by anthropologists, we have found several common characteristics, including faith healing, luck, superstition, propitiation of supernatural beings, and a cosmology. Apparently, to be human is to care how the physical world came to be, whether it has boundaries, and what is to become of it. Modern cosmology is a highly sophisticated subject funded by governments with hundreds of millions of dollars a year. It is unquestionably interesting, but is it, even in its modern guise, convincing? The modern paradigm of cosmology has it that the cosmos is expanding out of an early dense state, and that by looking outward in space we can, thanks to the finite speed of light, look back to much earlier epochs when the universe was comparatively dense and young. The Big Bang cosmology owes much to 2 accidental discoveries of redshifts in the spectra of distant nebulae by astronomers around 1920 and of an omnipresent background of microwave noise by radio engineers 1965, which is believed to be the remnant of the cosmic background radiation from a hot and distant past set in the theoretical framework of general relativity, Einstein's theory of gravitation, which is based on the idea that mass can curve spacetime. Such observations led to a model which makes predictions and can be tested by further observations. Of late, there has been much excitement over precision observations of the CBR and the discovery of very distant galaxies of great antiquity. There is even talk of a concordance model in which all of the observations have come together to paint a coherent picture of how the universe must be. And a greeting to Mr. Jetty89, and I want to acknowledge him for his very helpful comments on quantum mechanics, and I'm needing to brush up on it and stuff. Even when I went through grad school, I didn't quite comprehend. I was just deep in the weeds in math, and I didn't see the forest through the trees. I'd like to greet Wesley Coleman. Just a couple of points just at the beginning. It says cosmic background radiation. No one can actually formally prove it is omnipresent, quote unquote, as it says here. For all we know, it could be a local microwave background, and there have been even some people that that claim that there might not even be any background, that our instrumentation is being swamped by black body radiation coming from the water. This publication, Mr. Jetty asked, what is the date of this publication? Oh, I'd estimate about 10 years ago, or maybe even 15. I could look it up. Actually, Mr. Jetty, you could, if you look it up, you might be able to get a date on this. So I'm sorry. And but it echoes a lot of things that, you know, are my current understanding. So this is a good reason that this is one reason I like to put this out there, is this was, you know, there may be some that are more up to date, but this is actually very well written. And if anyone finds things in here that are obsolete, please feel free to comment in the side chat or video description, and this would be very helpful. It is true that the modern subject has taken a turn for the better, if only observers can now build instruments to deliberately test out cosmological ideas, where in the past cosmologists could only wait for serendipitous evidence to turn up. On the other hand, in order to explain some of the surprising new observations, theoreticians have had to conjure up heroic and insubstantial notions such as dark matter and dark energy, which supposedly overwhelm by 100 to 1 the ordinary universe we can actually detect. Interested laymen are bound to ask whether we should be more impressed by the new observations or more dismayed by the theoretical genies which have been conjured up to explain them. Oh, so this is published in the 70s. Okay. Well, if that's the case, some things have not changed. There is continued reservation about dark matter and dark energy. And inflation, especially inflation. So thank you very much, Mr. Jetty, that this was in the 70s. I actually thought it was only 10 years ago. So let's make this a historical reading then of a viewpoint from the 70s. And in my book, his viewpoint, his concerns have only gotten stronger. Oh, it was Mr. Jetty's question. Goodness. Let me see here. I'm going to try to settle this because I happen to know this is in Scientific American, I think, or New Scientist. Nope. Folktale. Okay, in American Scientist, this was in American, it was not Scientific American, American Scientist. And I'm looking at it now. And it would be my luck. American Scientist didn't put affix a date to this. The American Scientist one. Okay, this article was from the issue September to October 2007. So I'm going to. No, I'm really glad that Mr. Jetty pointed this out. So what I'm going to do is American All right, so this isn't, you know, most of these reading type shows are not the most well structured. I am looking to have kind of tighter presentations in the future that are a little bit more well crafted. So this is kind of a what I call the editing room here. So let me just dump this in the chat, in the side chat. And this is actually, this is going to be this is a more pictorial version of it. Okay, so here's the article. All right. All right. Our limited aim here is to discuss this dilemma by looking at the development of cosmology over the past century in order to compare the growing number of independent relevant observations on the one hand and with the number of also growing separate hypotheses or free parameters which have had to be introduced to explain them. Without having to understand the complex astrophysics, one can still ask, at an epistemological level, if, as you would expect of a maturing science, the number of relevant independent measurements has overtaken and comfortably passed the number of free parameters needed to fit them. All right, so just my commentary here. And anyone feel free to weigh in. The way that I read this is a free parameter is you're just making something up. You're just going to make it up to fix the theory. So, I mean, if I wanted to invoke God, does that count as a free parameter? I'm just pointing, guys, I'm just kind of pointing that out. And, you know, the thumbnail there was, you can Google Wonderful World of Disney, and there's a picture of Tinkerbell, the fairy. It's just funny that they had these. I had the opening with these football players in It's a Wonderful World of Disney. It's kind of mixing football and Tinkerbell. Anyway, so free parameters. I mean, could we just call stuff Tinkerbell or fairies or God? I mean, I'm just kind of pointing that out. The inflation field in particular is difficult because you're just invoking it. I don't know that there's any way we could test it. Because unlike operational physics, where you can test electromagnetic behavior right here on Earth with experiments, stuff in the deep past, you have a free parameter. So those are just kind of my thoughts. What you want to have is something that's at least consistent. And if you have a free parameter that violates operational physics, that's also very concerning. So that's one reason, at least I sense, and it's not just me, people are a little uncomfortable, definitely uncomfortable with inflation. Not, a little unease with dark energy, and dark matter has had some problems with confirmation. There is an experiment, and I wish I had kept track of this, with neutrinos and gravitational lensing. We got a neutrino detection that says that we expect to see a gravitationally lensed observation that'll happen in 2037, plus or minus 2 years. This would be an interesting confirmation or disconfirmation of the level of dark matter in the universe. There have been some earthbound experiments in 2019 that said the size of, we can't detect dark matter unless it's so small that it's beyond, it's really, really small. So again, this is not reassuring. And as I mentioned, I had professors both at my undergrad and graduate alma mater that were concerned about dark matter. And in the creationist world, ironically, or maybe unsurprisingly, there's also debate in the young Earth creation world community whether dark matter exists. Dr. Danny Faulkner insists that it's there, and you have a lot of other young Earth creationists that say no. So I'm like, okay, I'm going to say it's not to the level that I would believe it. I certainly, at this point, I don't think it's true. But let's just go on. So he's talking about these free parameters. So where were we? We do so, the number of relevant independent measurements has overtaken and comfortably passed the number of free parameters needed to fit them. We do so because we believe a discussion at this level can be appreciated by scientists from different fields, and indeed by all who are interested in the empirical approach. Lacking any such discussion, the layman has little option but to believe experts, who may be far too committed to supply objective advice. For a more technical critique of modern cosmology, see reference 4. In a robust astrophysical field such as stellar structure, there will be many more conformatory observations than free parameters. So what we want is we want to have way more measurements than we have free parameters, if it's a good theory. In contemporary cosmology, this turns out not to be the case. Indeed, as we shall see, the number of free parameters probably exceeds the number of relevant independent measurements, as it has done throughout history, with no sign of convergence between the two. Just because professionals cling to such a flimsy theory, there being no other within their current grasp, need not discourage the rest of us from being a good deal more detached. Okay, so compare what, like a robust theory, and even one we know is not exactly it has a domain where the approximation is valid. We know it's not exactly correct, but it's close enough that there's a lot of physics. That would be Newtonian mechanics, or more generally, classical mechanics. We have bazillions of experiments and measurements that confirm its behavior within the acceptable domain of macroscopic objects at speeds much lower than light, and kind of the gravitational situation we have on Earth. So that's a robust theory, even albeit it does have some caveats. Cosmology, especially Big Bang cosmology, is not that. Our starting point is a toy model of the scientific approach as it is applied to the physical sciences. On the one hand, experimentalists make observations with an estimated degree of uncertainty or error. On the other, theorists devise explanations or models to fit the observations as they exist at the time. And let me just look at this picture here. It's just kind of a general graph. And he's saying a toy description of the methodology used in the physical sciences. The theory should produce a mathematical curve which fits through the relevant observations where y, x of I, is a measurement, with error bars of the observable quantity x. The worse the fit, the less credible the hypothetical model is. The reverse is, however, not necessarily true. A model with enough latitude, i.e. with enough free parameters, i.e. parameters which can be chosen at will, can be made to fit practically any measurement. The theory will only be significant, likely to be true, if the number of its free parameters is comfortably less than the number of observations it has to fit. The need to introduce free parameters to fit new observations is not the sign of a robust theory. On the contrary. So okay, I'm not saying that this is, the Big Bang cosmology is just totally a lie, and people know better and they're not telling you the truth. When you're dealing with origin science, it's a different ballgame than operational theories like classical mechanics, quantum mechanics, electromagnetic theory, even geometric optics, which is one of the most ancient physical theories. And these can be, these can be curve fitted beautifully with very, very little error bars. In fact, there's so little that we pretty much regard them as laws at this point. The Big Bang cosmology is not like that. So let me go on. And by the way, when I pause, this is also a chance for me to kind of reflect on what he's saying. Such a theoretical model is expected to generate a mathematical curve which matches the observations as well as possible. The credence we grant to a theory depends, to a great extent, though not entirely, on the goodness of the fit between the theoretical curve and the available observations. So, okay, let me just pause here, and I need to mention Hugh Ross. God bless him. He was very essential to my return to the Christian faith when I had bouts of agnosticism about 22 years ago. But he bases a lot of his ideas on the Big Bang. Now, that being said, the young Earth creationists don't even have a model. So, I mean, they have a variety of models, and they have just probably, I'm guessing, they have lots of big free parameters. All right, so I'd say it's a level playing field. I just want to say, guys, just be careful before you argue. You're absolutely right. This is, try to distinguish when you're saying this is a faith statement versus insisting this is science. So I'd say this is especially true for the old Earth versus the young Earth creationist model. Although I really have to diss the theistic evolutionists. Their model doesn't agree. I think there's lots of it that's been falsified. So I'm sorry. You know, at least try to go with a theory that hasn't had so many falsifications as abiogenesis, or a theory that claims eukaryotic evolution is naturalistic. So anyway, off my tirade now. So let's get back to this. As I'm reading this, I'm sorry, I can only look in passing in the side chat, and I know I'm gonna miss some of the comments here. So let's just go forward. It is, of course, true that a sufficiently complicated mathematical curve can always be manufactured to fit any number of observations perfectly. For instance, if the curve had the polynomial form, and there you have it, up to 12 degrees there, where y x of I is the measured value of the physical quantity x, and the a, I, s are constants or free parameters, fp's henceforth to be chosen, then if we choose a polynomial with, say, 13 terms as above, we could always, by choosing the 13 fp's ai appropriately get a perfect mathematical fit of y x of I to 13 independent observations x. Since almost any theory with the same number of free parameters would make the same perfect fit, the observations lend no credence whatever to any of them. This is where the simplicity or parsimony of a theory comes in. Of the theories which match the observations, the simplest, i.e. the one with the lowest free parameters, is generally to be preferred. Why so? Because the probability of a curve with a smaller number of free parameters fitting a larger number of independent observations by chance is obviously smaller. If there's such a good fit, then the fit must be ascribed to something other than chance, to the probability that the theory behind the curve is actually true of the physical world. A high degree of such probability, a high significance in other words, is what the empirical scientist is hoping to find. Oops, let me get my, I'm going to comment here. Look at Newton's second law. It's F equals ma. I believe it's embedded because acceleration is a double derivative. This will relate to some mechanical theories, but a very large number of physics can be expressed in second-order differential equations. Second-order differential equations, a lot of them, unfortunately, are partial, so that makes it a headache. So my professor of mathematical physics, God bless him, Dr. Phil, I forgot what, we called him Dr. Phil. His last name, Edelman, Dr. Phil Edelman. But we called him Dr. Phil after the famous psychiatrist who's known as Dr. Phil. We affectionately referred to him. He said all laws of physics are only up to the second order. And I wouldn't be too dogmatic on that personally. I'd say a lot of the major laws are second order. So F equals ma, you have the second order derivative with acceleration being the derivative of position related to time. F equals ma. And there are other Maxwell's equations for second order partial differential equations. So even Schrodinger's equation, again, so many of the major theories are second order, and they end up being really robust theories. So in contrast, let's say someone came up with a theory of the stock market. He could come up with any number of he could absolutely curve fit with many terms. You just take a Fourier transform, no, a Fourier series. You could do a Fourier series or Fourier transform, and you just come up with an equation and just have a whole bazillion terms. You can curve fit it and say, hey, I got a theory. And then you have another observation and it just breaks that one down and you just rewrite the equation. So there was only one guy I know who had a really good theory of the stock market, and that was Ed Thorpe. And the scientific approach to the stock market, he actually became a filthy rich hedge fund manager, and he didn't try to curve fit. He used what is known as arbitrage. Arbitrage, you can look that up. So I was just thinking out loud there. A high degree of such probability, a high significance, in other words, is what the empirical scientist is hoping to find. Okay, so again, I want to emphasize, I'm not saying the young Earth creationists are free from this problem. Okay, so you don't build your house by burning someone else's down, right? But I am pointing out the Big Bang has these problems of free parameters. In practice, observation and theory usually march forward side by side. Observers make new observations, or better ones, with smaller errors, both of which reduce the probability of a chance fit between the theory and the new observations. In parallel, theorists are modifying existing models or introducing new ones, which have more or less free parameters. Both sides are, or should be, seeking to improve the significance of the fit to a point where further work seems unnecessary. And I'll point this out, evolutionary biology doesn't really even have, they're so post-dictive, it's all free parameters. And I can, I'm going to ask, how many integrated structures of a certain complexity of new proteins do you predict are going to happen over time? It's like, I don't know. Okay, then how could you predict like eukaryotic evolution could happen over a given amount of time? I mean, it's just all free parameters. It's a terrible theory. And worse, it's been falsified by just kind of an ordinary statistical analysis, just some common sense in cell biology. Goodness. All right, so another tirade, sorry. A short history of scientific cosmology. Since our main section will be employed in thus counting free parameters and measurements without attending much to their meaning, we here preface it with the briefest précis of the cosmological background. Scientific cosmology began with Kepler, 1610, who recognized that a space filled with stars could not go on forever, for that would imply a burning sky instead of the dark one we have. I think that's referencing Olbers' paradox. 3 centuries later, Einstein realized that his theory of general relativity, GR, implied that matter and energy could curve the space-time structure of the universe as a whole. That one could, for instance, imagine a finite universe, and yet one which is everywhere equivalent, with no center or edges, in 1917. This idea was philosophically attractive, for it potentially removed the need to worry about the boundaries. Unfortunately, or so Einstein thought of it then, general relativity implied that the universe would, because of gravity, either have to collapse or expand. So he found room, 1921, for a new free parameter, the so-called cosmological constant, omega, a sort of arbitrary anti-gravity, to put a stop to all that. Ironically, the observers, Slipher and Hubble, who were recording the first spectra of faint nebula at the same time, found that they were dramatically redshifted, hinting that perhaps the cosmos was expanding after all, though the expansion hypothesis remained contentious for 30 years, and Hubble himself died in 1955. Still skeptical of it, though most astronomers today seem to believe he actually established it. Astronomers found those dim nebulae to be immense islands of stars like our own Milky Way, called galaxies, at vast distances away. And that on its largest scale, the universe was made up of countless clusters of such galaxies, stretching away as far as telescopes could see. By the way, this was relating to the famous Shipley-Curtis debate about whether those little points of light are actually galaxies. That was actually a debate. Starling in the 1960s, Sandage attempted to carry out the program laid down by Hubble to use certain galaxies assumed to be constant standard candles to measure the age and curvature of the universe. Depth in the universe is very hard to gauge without assuming that such standard candles exist. Tinsley later in 1975 pointed out that Sandage's galaxies would evolve too rapidly to remain as standards. In 1965, Penzias and Wilson stumbled accidentally into the cosmic background radiation, a microwave whisper arriving from all directions of the sky. As we interpret it now, they were seeing optical radiation emitted by the gas of the universe when it was hot, 3,000 degrees Celsius, opaque and relatively young, 300,000 years old, redshifted through the enormous factor of 1,000 by subsequent cosmic expansion. This was looking into the past with a vengeance and seeing the remnants of what Hoyle dismissively called the Big Bang. But from now on, the expansion of redshifts was accepted, usually without question, as a natural expansion for the cosmic background radiation. And just as an aside, guys, it's not a done deal that the redshifts are the correct interpretation. I've seen some crazy stuff where people will say, well, the Lorentz transformation in the supernova confirmed that there's redshift and etc. There's a dilation, and then others say no, that was confirmation bias. I've seen, okay, so this is really technical here, and then I've seen where they said quasars don't have the right amount of time dilation relative to the redshift. I mean, it depends on which researcher you ask. All right, so I would say at this point, we're kind of in the unfortunate position where, unless we can actually send a spacecraft out there, which we're not going to, given the distances, at least we're not going to resolve it in several millennia, depending on, our current understanding of physics. We're kind of in an unfortunate position where we're just trying to eliminate order explanations. I'm just pausing there. I'm just pointing out some cautions here. The omnipresent cosmic microwave background can't confirm it. Absolutely. Same for the redshifts indicating expanding space. So I'm going to grant as much as I can for the sake of argument this is true. And I think Michael Disney will too. At the same time, astrophysicists sought to explain the origin of the elements. Ha ha ha. And that's what we were talking about in the last 4 weeks. Even assuming we have a Big Bang, we have all these other like R processes, S processes, P processes. I don't know. I put on the table Adamenko and Vostoyski's quantum attraction that can happen with high density electrons. So, we still don't know. And in a paper by Adamenko and Vostoysky and Miley, here in the United States, they pointed out the R process is still has more problems than it solves. So I think anything's game now. At the same time, astrophysicists sought to explain the origin of the elements. It seemed that most would come from the fusion of pristine hydrogen inside stars and be expelled into general circulation when those same stars exploded as supernova, spectacular short-lived events which can be seen out to vast distances. However, the lighter elements, in particular helium and deuterium, would have to form much earlier during the first minutes of the Big Bang. The theory of Big Bang nucleosynthesis set constraints on the number of baryons, the amount of ordinary matter in the universe. Dickey, meanwhile, noticed a worrying paradox in the Big Bang model. Antipodal parts of the cosmic horizon look accurately the same as one another, although they had never been in causal contact before. There had been insufficient time for a signal traveling at the speed of light to communicate between them. This difficulty was more or less unadmitted until Guth suggested, okay, I need to point out, this difficulty was unadmitted. So sometimes there's going to be a problem until someone will say, hey, I've actually fixed it. Now we can admit we actually had a problem. And Guth didn't actually fix it as far as I'm concerned. But anyway, this difficulty was more or less unadmitted until Guth suggested a vague conceptual solution. Inflation, a slow start to expansion followed by rapid acceleration. The necessary causal contact could then have taken place when the universe was young, but not yet flying apart too fast. If inflation actually took place, then sufficient stretching during the period of rapid acceleration would have lowered the local curvature today so that it would look flat to the observer, even if it wasn't so on a much larger scale, just as the Earth looks flat to an observer with a limited horizon. References 9, 10, and 11. And let me add to this, to pile on, inflation's in big trouble. Nobel Prize winners of the reputation of Roger Penrose are critical of it, and even one of the pioneers of some of the theories related to inflation. I covered it on this channel. His name escapes me now. He's critical of it. And just really, you know, the idea of the universe expanding at thousands or millions of times the speed of light. How are you going to prove that? That's free. That's a free parameter. Not to mention, it just kind of feels uncomfortable. All right, you know, they say, well, you can move stuff. You can quote unquote move it. It's more like inserting space at faster than the speed of light because we're inserting space. We're inserting space. You can then kind of effectively move things faster than the speed of light if you just insert space. It's like, okay, yeah, right. Let me just say, I think we're all entitled to some level of skepticism. And by the way, that's when variable speed of light theories began to come into play. They said, well, maybe this will fix at least one problem instead of inflation. And thing is, variable speed of light could fix a lot of problems for young Earth creation. Okay, so let's go on. In 1978, Bosma discovered that spiral galaxies are spinning far too fast to be held together by the self-gravitation of their detectable contents. There had to be far more dark matter than ordinary matter. Nobody knew what it was, but if the theory of gravitation was right at large distances, then dark matter was needed in spectacular amounts to hold the largest structures, such as galaxies and clusters of galaxies together. Such dark matter might well dominate cosmology, and was indeed welcomed by most cosmologists because it might be lumpy enough to get the galaxies formed in time. Another serious problem, as we will see next. Okay. Oh boy. Yes, and I've read Dr. Treffel's book, parts of it here on this channel. He was my professor of supplementary quantum mechanics in 2004. His book was probably written like 20 years earlier when I took his class. And he was saying he had a chapter there, the 5 reasons galaxies can't exist. So this is just like nothing new that isn't quietly acknowledged. The apparent uniformity of the Big Bang radiation, the CBR, led theorists to wonder how the present uneven structure of galaxies and clusters evolved out of such a smooth beginning. How the present uneven structure of galaxies and clusters evolved out of such a smooth beginning. Okay, so there have been some experiments with WMAP and COBE that kind of suggested maybe it's not that smooth. Okay, so just save that thought. That if you complain this is obsolete, okay, well, I'll just keep reading. There must have existed certain primordial fluctuations or elementary seeds of unknown origins, which somehow survived the early hot era when radiation would tear material things apart, and which then grew gravitationally during the more recent cold era, to finally collapse into the galaxies we see today. A type of dark matter that ignored the radiation, cold dark matter, or CDM, would make an ideal survivor which could condense into lumps, thereafter dragging the much lesser amounts of ordinary matter in afterwards, matter that would eventually light up as stars. By the 1980s, the theoreticians' universe was entirely dominated by such invisible entities. Meanwhile, the observers were building ingenious machines to measure what little could be seen to even greater precision. For instance, optical observers could measure the spectra of thousands of faint galaxies per night and look for their motions toward the supposed foci of dark matter. And microwave observers launched frozen telescopes above the atmosphere to measure the spatial and spectral structure of the cosmic background radiation to accuracies of parts per million. Instruments such as COBE, Boomerang, and WMAP, I mentioned the WMAP or Wilkinson map, have apparently measured the temperature, the spatial curvature, there is none, the present age, 13.4 plus or minus 0.3 gigayears, and also the angular spectrum of the primordial fluctuations, seeds, as they were all at a redshift of 1,000, with remarkable precision, a few percent. Precision, however, does not guarantee sound interpretation. Meanwhile, supernovae, which probed the universe at redshifts near 1, had an astonishing, almost shocking story to tell. 1998. The 25% dimming of such supernova suggested that the expansion, far from being slowed by gravitation, as had naturally been expected, had instead accelerated. Moreover, this acceleration had only started in comparatively recent times, 7 gigayears ago, halfway through the cosmic history. The physics responsible for this recent supposed acceleration is entirely unknown. It goes under the deliberately inscrutable name of dark energy. It may have something to do with Einstein's cosmological constant. When Adam Rees at Johns Hopkins, my graduate alma mater, spoke in 2013, he had a scheduled speech to give in 2013 at the Applied Physics Lab where I took my courses. And at the time that it was scheduled, he actually hadn't been nominated for the Nobel Prize. He won the Nobel Prize, and he arrived at his scheduled talk in 2013 to a packed out audience, and I was very honored to meet him. I met him at there was a nice reception there at the Applied Physics Lab. I got to shake his hand. About this inscrutable thing of dark energy, there have been some you can look it up in Wikipedia what it is, and like the cosmological constant, they said this is the worst prediction in the history of physics, because the numbers that one theory came up with is off by an order of 10 to the 20th fifth power. And in Dr. Rees's lecture, he said, yeah, my measurement disagrees with physical theory by that factor too. And everyone laughed. He said, well, okay, it didn't quite fit what people were expecting. And he left it at that, so I want to credit him for that. So look up the worst prediction in the history of physics. You'll see that. And Dr. Rees, who's credited with measuring this cosmological constant, this dark energy, also conceded that. So the cosmological observations we have now are fairly precise, and they even fit together coherently so long as we are willing to concede that the familiar baryonic material we can observe is overwhelmed by 20 times as much, or perhaps 100 times as much dark matter and dark energy, which for the moment are no more than ad hoc theoretical contrivances. Let me just okay, so look at the cosmological constant problem. The discrepancy, you can Google this. Maybe I'll dump it in the chat just so you could see it. 120, I said 125. It's 120 orders of magnitude, which you could say is 10 to the 120th off. And it said, this is the largest discrepancy between theory and experiment in all science, and the worst theoretical prediction in the history of physics. Oh boy. So I'm sorry to laugh. Okay, so that's why there's a saying, there's cosmology and then there's speculation. There's speculation and then there's cosmology. Let me just dump this in the side chat. We now return to the preoccupations of Section 2, the significance of cosmology. That is to say, the difference between the number of measurements with cosmological relevance that have been made and the number of free parameters introduced to fit those same measurements. Where that difference is comfortably positive, one might regard cosmology theory as significant in the sense that that the fit may be better, perhaps much better than one could have expected by chance. But where it is zero or negative, there is no such balance of probabilities to recommend it. Precisely which and how many free parameters are regarded as cosmological, as distinct from more widely astrophysical, is to some extent a question of taste. But it does not matter so long as we treat them consistently. I.e., if we included for fitting, they also be included for measurement. We follow the prescription adopted by the WMAP team, reference 14. We proceed by means of an historical table where each line introduces either new free parameters, column 3, or the first, seldom the best, claimed measurement of them, column 4, with a concurrent difference in the number between the two, the concurrent significance, in column 5. This is purely a counting exercise with no real need to understand what the parameters are. Okay, this is purely a counting exercise with no need to understand what the parameters are or how they have been measured. Readers interested in such details can follow them up in the notes, numbered corresponding to the lines in the table, to be found on the line in the online supplementary materials. Okay, 1917. Column 2, new step. Column 3, the number of free parameters. Column 4, the number of measurements. One equation between them. So they have a current significance of -2. I'm just going to go through these. Cosmological constant, -3. Galaxy redshift, -2. Cosmic background radiation, -2. Big Bang nucleosynthesis, -2. Cosmochronology, -2. Dark matter, -3. Initial seeds, -5. Gravitational waves, -6. Inflation, -7. Oh! Yeah, I told you inflation's in big trouble. Large scale structure, -10. Oh my goodness. Okay, I guess this is talking about like things like the galactic strings of superclusters. COBE, -9. Supernova, -9. Clustering, -8. Galaxy infall, -7. Boomerang, -4. WMAP, -4. Okay. I guess you want to get something above 0? At least 0, preferably above it. So the situation today, 2006, is that the currently fashionable model of cosmology, known as lambda CDM, is cognoscenti, has 18 free parameters, only 17 independent. 13 of these parameters are well fitted to the data at the 5% level and sometimes better. The gravity wave parameter R is vague, while the quadrupole parameter tau naught, inflation n, and the dark energy parameter W remain floating for now, leaving the net significance of -4. To say the least, this is far from healthy. Worse still, there is no sign of a systematic improvement over time. Even 3 successful predictions of apparently flat space by inflation, of the light element abundances by nuclear theory, of the maximum ages of the oldest star clusters by expansion, are overbalanced by at least half a dozen of the unpredicted surprises: redshifts, cosmic background radiation, dark matter, inflation, dark energy, and no CBR quadrupole. I guess what he's saying is you could fit some things if you allow other things to not fit, to just be free parameters. Of course, there are many caveats, some pro-cosmology, some anti. On the pro side, the counting of independent measurements is not trivial. Modern instruments make measurements not in a single channel, but in the spectrum of channels within a given dimension, e.g. wavelength. This could increase the information returned by as much as the logarithm of the number of such channels by several. On the anti-side, note that we have been counting only the number of free parameters explicitly admitted within the theory. But the Big Bang cosmology, BBC, is not a single theory, but 5 separate subtheories constructed on top of one another below. Each was selected out of an essentially infinite set of alternatives to fit the observations as we know them at the time. By rejecting the alternatives, one is, in effect, fitting several extra implicit free parameters in each case. These extra conceptual free parameters should arguably be added to the totals in Table 1, perhaps 2 or 3 for each subcategory, reducing the total significance by 10 or more. This is why such a counting exercise can never be precise. The caveats are, however, arguments at the margin. A healthy theory with a large positive significance could afford to ignore them. Cosmology, with its formally negative significance, must remain for now a bloody tilting ground for its propagandists and skeptics. Significance must remain for now a bloody tilting ground for its propagandists and skeptics. By the way, his English is fabulous. Tilting is, I believe, jousting in, the middle of the knights trying to kill each other. Yeah, he has beautiful writing style in addition to being an astronomer. Wow. BPC, that is Big Bang Cosmology, is not a single theory, but 5 separate theories constructed on top of one another. The ground floor is a theory, historically but not fundamentally grounded in general relativity, to explain the redshifts. This is expansion, which happily also accounts for the cosmic background radiation. The second floor is inflation, needed to solve the horizon and flatness problem of the Big Bang. And incidentally, inflation also tries to solve a problem in grand unified theory with magnetic monopoles. That's in my cosmology book, just adding that. The third floor is the dark matter hypothesis required to explain the existence of contemporary visible structures, such as galaxies and clusters, which otherwise would never condense within the expanding fireball. The fourth floor is some kind of description for the seeds from which the structure is to grow. And the fifth topmost floor is the mysterious dark energy idea needed to allow for the recent acceleration of the expansion, apparently detected in supernova observations. And I need to point out, not everyone agrees with Professor Reese at my school, that his interpretation of the supernova is actually a measure of acceleration or dark energy. It's still contested, and some professors who will not be named at that said school, since they're Dr. Rice's colleagues, are also, they have some reservations, to suffice to say that. It's preferable if a Nobel Prize, after it's awarded, has less and less controversy as it's more confirmed. So I think, like, for example, the photoelectric effect has really good confirmation, which Einstein got his Nobel Prize for. Same for Planck. As far as I know, it has lots of confirmation. Dark energy does not. So, can they take back a Nobel Prize? Thus, the dark energy floor could crumble, leaving the rest of the building intact. Yeah, the dark energy floor could crumble indeed, leaving the rest of the building intact. But, by the way, this is a really good description. This is a really good description. We can criticize parts of this. We could blow, we can blow away inflation and still have an expanding universe. Okay. But if the expansion floor collapsed, then the entire edifice above it would founder. Expansion is a moderately well-supported hypothesis consistent with cosmic background radiation, with the helium abundance and with various chronologies in our locality. However, finding more direct evidence for universal expansion must be of paramount importance. This is going to be good. In the 1930s, Tolman proposed such a test, really good data for which is only now becoming available. Tolman calculated that the surface brightness, the apparent brightness per unit area of receding galaxies, should fall off in a particularly dramatic way with redshift. So dramatically, in fact, that those of us building the first cameras for the Hubble Space Telescope in the 1980s were told by cosmologists not to worry about distant galaxies because we simply wouldn't see them. Imagine our surprise, therefore, when every deep Hubble image turned out to have hundreds of apparently distant galaxies scattered all over it. Contemporary cosmologists mutter about evolution, but the omens do not necessarily look good for the Tolman test at high redshift. If expansion were to fail, then so would the entire superstructure. I'm going to read this again because I've heard critics of the Big Bang invoke the Tolman test, and I haven't heard very good responses. This is really important. In fact, this is why this article in particular caught my attention, because he talked about the Tolman test, and I had seen some things related to Tolman in my cosmology book. And, you know, at the time, I mean, it's still kind of hazy what the professor was trying to teach me. And he was kind of relating Z, which is the amount of redshift, to some other things. And I was like, yeah, you know, okay. Just give me the equations and I'll just recite them on the exam. You know, it doesn't mean I have to actually comprehend what you taught me. I'm sorry to be disrespectful there, Dr. Najmi. Yeah, by the way, my professor of physics, he was Richard Dawkins' drinking pal in the 1980s in the pubs over there in Britain. Just total, that was a rabbit trail. Anyway, I'm going to read that passage again, guys. This is probably the best part. And if anyone has any other data points to try to explain this away, I'd be interested. However, finding more direct evidence for the universal expansion must be of paramount importance. In the 1930s, Tolman proposed such a test, really good data for which is only now becoming available. Reference 16. Tolman calculated that the surface brightness, apparent brightness per unit area of receding galaxies should fall off in a particularly dramatic way with redshift. So dramatically, in fact, that those of us building the first cameras for the Hubble Space Telescope in the 1980s were told by cosmologists not to worry about distant galaxies because we simply wouldn't see them. Imagine our surprise, therefore, when every deep Hubble image turned out to have hundreds of apparently distant galaxies scattered all over it. Contemporary cosmologists mutter about evolution, but the omens do not necessarily look good for the Tolman test at high redshift. If expansion were to fail, then so would the entire superstructure. In its original form, an expanding Einstein model had an attractive economic elegance. Alas, it has since run into serious difficulties, which have been cured only by sticking some ugly bandages, inflation to cover the horizon and flatness problems, overwhelming amounts of dark matter to provide internal structure, and dark energy, whatever that might be, to explain the apparently recent acceleration. A skeptic is entitled to feel that a negative significance after so much time, effort, trimming is nothing more than what we would expect of a folktale constantly being re-edited to fit inconvenient new observations. Is nothing more than we would expect of a folktale constantly re-edited to fit inconvenient observations. You know, I got to say here, okay, people ask me why I'm a young Earth creationist. Even before I read this article, which is after I finished my grad studies, there were all these whispers among the professors, among the grad students. And it's like, okay, you're kind of admitting this informally, and yet this is textbook stuff. And so I've always kind of sensed, you know, there are all these, like, you know, mutterings. This is uncomfortable. And thankfully at my undergrad alma mater, George Mason, there were 3 bold professors that came out and said exactly this. And that I mean, they used a lot of terminology I didn't understand, and I'm still hazy on the meanings of all this. but it sounded credible enough. I said, I think I want to study cosmology. And I had the privilege of studying it. Not that I really comprehended much afterward, but I said, I want to understand this debate. And the more that I studied it, it's like I got the same feeling that this is on shaky ground. And that led to my shifting from being an old Earth creationist to a young Earth creationist. Now, one could say, Sal, you could just be agnostic, and I as to those questions, and I could say that's definitely an option. I know there are some people who identify as creationists and are not committed to one particular model. So, I'd say that's fine if you feel in good, in your conscience that it reconciles with your interpretation of scriptures. That's fine. I have to say that because I was working on the genetic entropy problem, it really did seem human life could not have evolved over millions of years, especially now looking at the complexity. So I would have to invoke something like progressive creationism. So it's either progressive creationism or what I think is a little more parsimonious, and that's subject to debate, young life or young Earth creationism. But again, I'm saying I perfectly respect if someone's going to be agnostic about all this. Clearly, you could see we don't have enough data. We really don't have enough data. Everyone's kind of arguing in a vacuum, and we don't have all the observations that would really kind of reassure us one way or the other. So I'm just throwing this out, and this is really a great article. A folk tale constantly re-edited to fit inconvenient new observations. Professional cosmologists tend to put an entirely different gloss on the evidence. Reference 17. But with a negative significance, they could well be deluding themselves. Just because an alternative hypothesis is not presently in sight, and it is not, does not mean we have to accept the only vaguely possible one to offer. It was thus that witchcraft took hold. They may be forgetting that dimensional constraints alone can lead widely different theories to predict closely the same quantitative results. For instance, the predominant scale of the patchiness of the CBR. Any precision is not equivalent to reliable interpretation. Any precision is not equivalent to reliable interpretation. And the chief concordance of Big Bang cosmology, which so comforts some cosmologists, namely the summation of densities, omega A, omega M, omega H, or omega B, so close to +1, the value necessary for a flat or inflated space would indeed be impressive if only more than 0.5% of the sum were made up of physically detected entities. Okay, let me just pause to uncoil this. This is a little complex. You could have two different theories looking at the same observations. I'll give two examples. The easy one is the bent pencil in water. You can come up with a theory that the pencil is bent, or a theory that somehow the water is changing, is refracting the light waves and therefore giving an illusion. So you can come up with two theories. They would both, they would both fit observations to some extent, until, of course, you come up with a different observation that can resolve the discrepancy. A much more significant one was heliocentrism versus geocentrism. Geocentrism would explain a lot of observations coherently and consistently if you had epicycles. Heliocentrism had a lot less free parameters and has agreed with all of our observations to date. And it's more sensible. There've been, I often say, okay, you can see the difference in the quote-unquote gravitational acceleration at the equator versus at the poles. You also have the Coriolis effect. So you detect these fictitious, quote-unquote fictitious forces, the Coriolis effect, and centrifugal forces at the equator. That's consistent with heliocentrism, or at least it's consistent with the Earth rotating. And so the idea is, that's kind of a way of seeing how you want to reduce the free parameters. Heliocentrism has very few free parameters. Snell's law, which explains the bent pencil, agrees with the abundance of measurements. Otherwise, you'd have to generate all these ridiculous free parameters to say that the pencil is actually bent when it's dipped in the water, and worse yet, it's unbent when it's removed. So they're talking about all these omegas here being close to 1, and they said it would be impressive indeed. It would indeed be impressive if only more than 0.5% of the sum were made up of physically detectable entities. They're saying 99.5% of all that theory is based on stuff we can't detect. That's not good. Maybe stuff we can't even detect in principle, which is really bad. And the apparent observation that cosmic deceleration has only recently switched to acceleration places us, from a Copernican point of view, in an awkwardly special moment of time, e.g. 18. This is the so-called crime of fine-tuning, and there is another more sinister pressure at work. Some, particularly in the space agencies, worry that the general public is insufficiently interested in space astronomy to pay for it, unless they are promised future certainties as to the origin of the cosmos. Even if it were ethical, it is dangerous to make promises based on such weak evidences. Okay, so we're at an awkwardly special moment in the time of the universe. Lawrence Krauss alluded to this. It's sometime in the distant future. We're at such a special time in the universe that if the Big Bang is true, we happen to be at the one time alive in the universe where we could establish it as true. Future generations, when the galaxies is spread out enough, will not be able to detect what we are detecting now. Hence, they'll actually come up with the wrong inference to the truth of origins. Now, that has to be, at a philosophical level, kind of like disconcerting, because then we're like, well, how do we know that we're at the right place in the universe and not making the wrong inference? Maybe some other generation is actually going to make the right inference. We just happen to be in the wrong spot. I mean, this has a lot of philosophical implications, and this is where I laughed about, when they're just hammering about science. I said it's not always going to work. There's one example there. You have one scenario, and granted, okay, I'm only doing this for the sake of argument because I don't believe in the Big Bang. But if you accept it, you have a scenario there where evidence and reasons is going to lead you to the wrong conclusion. Evidence and observation and reason and experiment is going to lead you to the wrong conclusion. The scientific method is predicted to fail, according to Lawrence Krauss, at some future time in the universe. Now, philosophically, if you accept the scientific method on faith, that's an unacceptable situation. And this also leads to kind of philosophical and religious ideas. Are you going to accept a theory that is going to say the scientific method will fail at some point in the universe, at some time in the universe? That's a faith decision. So that's what Michael Disney was referring to about this awkwardly special time. We are at an awkwardly special moment in time of history. And that's another talk right there. So, or you could say we're just miraculously created at a special time, and Christ died at the right time. I mean, you can interpret it all sorts of ways, but I would just say, do we want to give up faith in science? That it, okay, you're going to have to give something up if you take the Big Bang. Just think about that. Just think about that. So, non-cosmologists are entitled to remain skeptical of the so-called precision version of Big Bang cosmology, even though it fits much of the data rather well, and some aspects of it, such as expansion, are far more robust than others. Given the number of its free parameters, 17, so it ought. Okay, it's supposed to fit that because you have all these free parameters to help it out. It may be healthier as well as more exciting to admit that we are surrounded by great mysteries which will provide challenges for generations to come. More fundamentally, as Daniel Boorstin, the historian of science, remarked, the great obstacle to discovering the shape of the Earth, the continents, and the oceans was not ignorance, but the illusion of knowledge. Imagination drew in bold strokes, instantly serving hopes and fears, while knowledge advanced by slow increments and contradictory witnesses. Oh, this is a beautiful quote. I'm just going to read it again. The great obstacle to discovering the shape of the Earth, the continents, and the oceans was not ignorance, but the illusion of knowledge. Imagination drew in bold strokes, instantly serving hopes and fears, while knowledge advanced by slow increments and contradictory witnesses. And if I may bash evolutionary theory again, as you know I love to do, evolutionary theory is an illusion of knowledge. It is hindering advancement in understanding at the operational level with junk DNA. And now, I'm going to point out that the nested hierarchies are the consequence of biology designed, optimized for scientific discovery, such as things like protein folds. And I'll be doing a talk on that. This is why, if you're a young Earth creationist, you can be so privately and in church and among your friends and say, I really believe this, and these are the reasons why. Publicly, kind of what I'd say professionally, I'll say, okay, maybe at most I can get all sides to reconsider that maybe we have an illusion of knowledge for things like evolutionary theory, for things like nucleosynthesis, which affects radiometric dating, maybe the speed of light. There's a lot we don't know. Why don't we keep an open mind? And maybe that's about, the most diplomatic way to approach this for people that don't share my views on young Earth creationism. And I hope we've had a fun time talking about stuff like heavy electron quasi-particles, where I just throw stuff in there that I think is relatively well supported and, opening up new horizons. Anyway, if we are not appropriately skeptical about cosmology today, then the current myth, if myth it is, could likewise hold up progress across all of extragalactic research for generations to come. If we are not appropriately skeptical about cosmology today, then the current myth, if myth it is, could likewise hold up progress across all of extragalactic research for generations to come. So I'd like to thank everyone who's joined us here. I'd like to thank Mr. Jetty for pointing, kind of prodding me to find out the date of this article, circa 2006, 2007. Everything that has transpired since then has not been very reassuring to the Big Bang. As I said, it's coming apart at the seams because we're seeing this in peer review. The dirty laundry is starting to come out, and it's starting to stink too. So I think it's an exciting time. Wherever anyone is on the spectrum of the creation evolution controversy, um, I think we live in exciting times because there are bold new frontiers, and we can start to think of new theories that may actually help reconcile the observations we're arriving at, and the measurements we're making, and the experiments. Um, I do feel that some experiments, especially since I'm interested in low energy nuclear reactions or a quote unquote cold fusion, sometimes um, sometimes thinking out of the box and maybe saying, hey, there could have been experiments out there that don't agree with, our illusion of knowledge. Let's admit it. And I've seen this cold fusion thing develop over 30 years. And, now we're having more and more accepted experiments that are appearing in good journals and appearing in good institutions like NASA. So this is an exciting time to be alive. Let me then try to wrap up and connect this to the Christian faith. I said at the opening, the kingdom of heaven is like a treasure hidden in the field. And in the modern day, the way we discover hidden treasures of the past is through the lens of science. And that's why we study science a lot here. Yes, it'd be easier for us if the Lord chose to be as apparent to our senses as the air we breathe or even the people we know in person. If, I was considering the New Testament. Jesus appeared to first his apostles and then 500 chosen people to be his witnesses. By the way, the Greek word for witness is martyrs, okay? Just to let you know, if Jesus works a miracle for you and does something convincing, just be aware you might be on the hook to live your life to a certain higher standard, because to whom much has been given, much will be expected. And this is sobering for us who have sought to learn evidences for the Christian faith. As you learn it, you realize, oh my, I have to live my life to a different standard now, because we will be judged more harshly. So where I was going with that, we had the 500 witnesses. Why didn't Jesus just appear to everyone? And I believe it is the Lord filtering out those who really love him and want to be with him for eternity. We show him that we love him by seeking after him. And it could be for the doubting Thomases, as I was, just to love the idea enough to pursue it. I've met some atheists that said, well, even if God were true, they'd rather go to hell than serve the Christian God. It's evident they have no love of God or even the idea of God enough to pursue him. So I think that's why some of this is hidden. And we've been blessed with modern 21st century science to help us investigate the questions of the origin of the universe, the miraculous origin of the universe, and the miraculous origin of life. We can go one step further and consider things like, do we have scientific evidence for a literal interpretation of Noah's flood and the literal interpretation of the genealogy of Christ? But I hope this show has maybe given all of us some reasons to consider a variety of things. And I know some of my critics have always wondered, how could someone that has, kind of Sal's background in secular science believe in young earth creationism? A simple answer is, it's really hard for me to believe in the mainstream models right now. I don't trust them as far as origins. And it made it easier for me to, one, believe at least in old earth creationism, and secondly, in a young life, young fossil record, young earth, young solar system, young cosmos, and it'll remain to be seen. And I'm excited about potential experiments and observations in the future that will bring us closer to the truth. I believe God is bringing us closer to the truth. We live in the last days, and I'm not saying like next year or 100 years. We don't know when the Lord will return, but in these last days, to use the New Testament phrase, I believe God is giving us the evidence we need to reassure us that Jesus is Lord, that he rose from the dead, and that God's word can be trusted. So with that, I'm going to close with my favorite poem. Take care, and the Lord richly bless you.
I have slipped the surly bonds of earth and danced the skies on laughter-silvered wings. Sunward I've climbed and joined the tumbling mirth of sun-split clouds and done 100 things you have not dreamed of. Wheeled and soared and swung high in the sunlit silence. Hovering there, I've chased the shouting wind along and flung my eager craft through footless halls of air. Up, up the long, delirious, burning blue, I've topped the windswept heights with easy grace, when never lark nor even eagle flew. And while with silent, lifting mind, I've trod the high, untrespassed sanctity of space, put out my hand, and touched the face of God.